some of you in the class have experience more in the fields, some people have more experience in the greenhouse, and some of you are new to horticulture and soils altogether. It's easy to think that the same characteristics of what makes good soil in the field would also lead to good soil in containers, but it's helpful to start this class out by remembering that it's in fact such a different environment. So we're really catering to the roots of plants here, and often the roots of really baby plants as we grow them from, germination stage upwards. So thinking about the root environment, we're remembering that it's artificial. Therefore, your plants, your roots will require more irrigation, more moisture than they would out in the field. It's a much smaller environment. They can't draw on the soil around them. All they have is what is in their container. They require fertilization way more often than plants in the field for the same reasons. They don't have much to draw from. The space, it's a reduced volume, and it's affected by the composition of the media. And this is what we'll be focusing on for a lot of this class. Before we can learn to be good managers of media for container growing, we need to understand the primary functions of the media, the physical and chemical properties of each different ingredient, some basics about plant nutrition, what they need and how they get it, and proper sanitation. You'll hear a lot of terms thrown around that are in fact usually referring to the same thing. So when talking about media, we're talking about the growing medium. We're talking about soil, except of course, all these mixes don't necessarily contain soil, but they're taking the place of soil in the containers. People will throw around terms like seed starting mix and potting mix, and technically those mixes all have different elements, which we'll talk about, but casually people might kind of interchange them. So the mix of ingredients used to support root and plant development is the definition we're working with. Most often, the media is soilless, which means it doesn't contain any soil, often doesn't contain any nutrition, which is something we touched on in our midterm a bit. And we're using specific recipes designed to create the best environment for plant growth. So we will have general use mixes that can cover a broad range of plant types at a broad range of stages, but some plants, especially at some stages, require specificity. Let's take a look at the primary functions of media. So first of all, we're thinking of how this substance is supporting your plants. Second of all, we're thinking about aeration, the airspace that is distributed throughout the container for the roots. Third, water holding capacity. And fourth, minerals and nutrients. So let's drill into water holding capacity, nutrition, and airspace. Container-grown plants require the same nutrients as plants out in the field, but we're working with a much smaller man-made container, and how are we going to get the plant what it needs? The supply is, of course, limited by the container size, so we need to maximize the nutrition inside of this container. When dealing with nitrogen, we can apply nitrogen through powdered slow-release fertilizers, or we can inject them into the irrigation system, often known as irrigation. So we're thinking not only about fertilizer, but also about pH, what pH is favorable for these plants, and what structure will provide aeration for the roots and also permit water infiltration and movement throughout the container. Here's a little visual to help us get used to thinking about the different sizes of these components, these ingredients. So you see these tiny clumps of vermiculite particles compared to peat particles. So one is much smaller, one is much bigger. So we start to think about the airspace created by these different sizes of particles and their ability to allow water to flow through. Since the size of the pore space is determined by the size of the particles, we can really manipulate this environment according to our plant's needs. So increased pore size increases drainage. So if your goal is to increase drainage, let's say if you're growing a cactus, You could consider using pumice instead of sand. The bigger the particle, the more pore space. If your goal is to improve root anchorage and prevent containers from blowing over, in that case, you might want to use sand, therefore less airspace, heavier containers. So when it comes to different choices in water holding capacity, water needs to replace a loss of moisture from transpiration. Roots need a supply of oxygen in order to absorb the water. So because containers are fairly shallow, standing water develops and collects at the bottom of the containers. The finer the texture of the media and the shallower the container, the higher the moisture holding capacity and the lower the aeration. Conversely, the coarser the media texture and the deeper the container, the better aeration and poorer the moisture holding capacity. So here we can start to see that different pot sizes, in fact, require different potting mixes, different media. So media particles at the bottom of the container are able to hold on to more moisture. Therefore, container height affects the relative amount of water versus air. With the same media, the perched water table occurs at the same height regardless of container size. So short containers will have the same perched water table level as large containers. This explains why a 5-gallon container holds less water than a 5-gallon squat container. So the size and shape of the container really determine a lot about the moisture holding capacity. Let's dive into some different media ingredients. Many of you are familiar with this from your sustainable agriculture courses or from gardening. So in thinking about soil outside, we generally refer to clay, silt, and sand. Clay being the smallest particle size, silt being in the middle, and sand being the largest. So many of you are familiar with these different particle sizes from just gardening. Sand, as we know, generally is pretty poor in fertility and little moisture retention, but of course, the drainage is incredible. Clay, on the other hand, is very high in fertility, high moisture retention, yet the drainage is horrible. So I think back to the first place I farmed in Petaluma. It was that typical adobe clay, and it was a pain in the butt to work. We had to wait forever in the spring for the soil to dry out. But the fertility was amazing. Plants just wanted to grow, and I felt like any nutrition, any fertility we added to the soil just stayed there. Silt is kind of in the middle, right? So there's some fertility, some drainage, about halfway between the other two. So let's focus in on some of the most common media ingredients. Sand as an ingredient is great if that's what you need. It's super cheap, provides great anchorage. There are, of course, different grades of sand. So if you're looking for a lot of drainage, you want coarse sand rather than fine sand. Peat moss has its benefits and its drawbacks. So it has great water holding capacity. It's available in different particle sizes. However, as many of you know, there are a lot of problems with peat. It's just not sustainable. We've been draining peat bogs, which take forever to renew. So it's great to move away from peat moss here. We have some substitutes. Composted bark is a timber byproduct and can stand in. And coconut coir is what I've used extensively. It's pretty hard to wet, but once you know how to work with it, it can work pretty well. A few more wood products include aged sawdust, hardwood bark, and pine and Douglas fir bark. Moving on to mineral ingredients. Perlite and vermiculite are two standards that we will use over and over again and refer to a lot as well. So perlite, it's lightweight, it's a granular material made by heat treating crushed lava. Comes from lava, which is pretty cool. It's sterile and it's pH neutral, great water holding capacity, no cation exchange capacity, and it's used to decrease the weight and increase aeration. So often in a nursery, if you pick up a pot and it's a lot lighter than you thought it was going to be, there's probably a lot of perlite in it. I don't know if any of you confuse perlite and vermiculite. They're both used commonly, but I like to remember that perlite looks like little pearls. There you go. So vermiculite is lightweight. It's a plate-like material, and it's made by heat treating mica. It's the same weight as perlite, good water holding capacity, good CEC, and it avoids compression when wet. And here is a table for your reference of different chemical and physical properties of some common materials. So bulk density, porosity, pH, and cation exchange capacity. That's it for today. Thanks.